Okay, so chapter 5, we really started diving into identities and manipulating around trigonometric functions and equations. We start talking about solving and proving different things. So I don't know if you remember back in high school when you took geometry, but you probably encountered like 2-column proofs where it would tell you something equals something and you have to prove it. You're going to do that in trig. You're going to have basically 2-column proofs where we are going to manipulate a trigonometric expression or equation and try to make it look like something else. And we're going to use a whole bunch of different identities for this. Now, I have told you all semester I am not super mean. I don't expect you to memorize every single one of these identities because you're going to get more. Like, these are not the exhaustive list. But some of these you should know. Some of them, like the reciprocal identities, you should know those. The quotient identities are nice to know. If you know the Pythagorean identity, at least the sine squared plus cosine squared theta equals 1. That's kind of a big one. But when it comes to taking a test, this is where I will provide formula sheets for the exam on what I feel like you should have access to. So I'm not going to be a big meaning and expect you to memorize all of these. But you do need to be able to look at them and use them to manipulate your functions around. So the very first set of identities is just talking about even and odd functions. This is back from college algebra. This was also one of the kind of listed information under all of your graphs from chapter 4 material. So if you have an even function, that means if you have f of negative x, it's the same as f of x. So even functions are symmetric about the y-axis. If you fold it over the y-axis, it's the same because your y's aren't changing, just your x values are. If you are an odd function, that's f of negative x equals negative f of x. What that means is you are symmetric about the origin. So everything in the upper right-hand quadrant becomes in the upper or the lower left-hand quadrant and vice versa. Those are even and odd functions. The reciprocal identities are basically the definitions of those cotangent, secant, and cosecant trigonometric functions, where cotangent is 1 over tangent, secant is 1 over cosine, and cosecant is 1 over sine. Your quotient identities, tangent theta is sine theta over cosine. So that one may be a little bit new or different that we haven't really played around with. Cotangent then, since they are inverses of each other, will be cosine over sine. If you get confused on those, because we are using cosine and sine to talk about tangent and cotangent, it's kind of alphabetical in that if you're talking about tangent, then sine's on top and cosine's on bottom. If you're talking about cotangent, then cosine is on top and sine is on bottom. So both of the C's are on top for cotangent and cosine. Then we have a whole bunch of Pythagorean identities. Really, though, even though it looks like there's 5, we have 3, and then these 2 over here are just manipulations of the first. And we could do manipulations of the other 2 as well if we needed to. Sine squared theta plus cosine squared theta equals 1. That comes directly from our unit circle when we looked at our x's and y's and we talked about them in terms of our sines and our cosines. So that's where that is being derived from. These 2 over here in the second column are just manipulations of the first. So I had got sine squared by itself. That looks like 1 minus cosine squared. Then I got cosine squared by itself, which is just 1 minus sine squared. Just manipulated the equation. Then there's tangent squared theta plus 1 is secant squared theta, and 1 plus cotangent squared theta is cosecant squared theta. The last set of identities are even and odd identities. So this is kind of where you can see which of our functions are even and which of our functions are odd. If sine of negative theta is negative sine of theta, then if we look up here at our even and odd, that means that sine is an odd function because we put in a negative and we take the negative out front. Cosine, on the other hand, is an even function. Cosine of negative theta is cosine theta. Tangent is odd, cosecant is odd, and cotangent is odd. So our only even functions are cosine and cosecant, or excuse me, cosine and secant. That's really all the notes. Now we're going to do some problems where we're going to find different trigonometric functions based on the information that they're going to give us. So they're going to give us bits and pieces, and then we're going to use all these different identities and all this different information to try and manipulate a function around to look like something else, is what we're going to do. I'll try and leave some of it up there, at least for the first problem. Says if tangent theta is negative 5/3 and theta is in quadrant 2, so those are our stipulations. Tangent theta is negative and theta is in quadrant 2. We need to find secant of theta. And let me go ahead and tell you that for a lot of the stuff in Chapter 5, there's going to be more than one route to get there, because you could use different identities to get you to the same ending point. So if I show you a way here, but you're thinking of a different way, that doesn't necessarily mean your way is wrong. As long as you're using the identities to get you where you need to go, then you're going to be okay. So we need to get to secant theta. But we're starting with tangent theta. So let's look at our different identities here, and let's see what we've got. If I look at my Pythagorean identities here, notice I have tangent squared theta plus 1 equals secant squared theta. That has both of the parts that I kind of need. I can start with my tangent. I need to end up with my secant, so I'm going to start with that one. Tangent squared theta plus 1 equals secant squared theta. Well, in the instructions, it's telling me that tangent is negative 5/3. So I can plug that in here. Negative 5/3 squared plus 1 equals secant squared theta. If you take negative 5/3 and you square it, then you're going to have 25/9 plus 1 equals secant squared theta. Get a common denominator, add that 25/9 to 1. You get 34/9. So if 34/9 equals secant squared theta, how would I get just a secant? Yeah, you square root both sides. All of the rules that you have in algebra hold in trigonometry. We're not making up a whole new class of math. We're just doing it in a slightly different format. So to get rid of the square, you would square root both sides. 34 isn't a perfect square, but 9 is. So I have 34/3 equals secant theta. Now, before we just assume that we're done, they did give us a stipulation that theta is in quadrant 2. So I need to understand if secant in quadrant 2 is positive or negative. And I know it's been a hot minute, so I'm going to show you. Back in 1.4, we had this table. of signs of trigonometric function values, where we had our different quadrants, and then we had our 6 main trigonometric functions, and we determined whether those were positive or negative based on the different quadrants we were in. And so the nice thing was that everything was positive in quadrant 1, but then it started to change as we got to our different quadrants. And that had to do with the fact that sine and cosine represent your x and your y values in your different quadrants. So if I'm thinking about secant, which is this column, and I'm in quadrant 2, secant has to be negative. So I have to have this table, or I have to recognize this and have this knowledge so that when I solve, I realize that I have to put a negative out in front of this value because it's specific to quadrant 2. So we pick our sign based on the information that they give us and based on whether or not that trigonometric function is positive or negative for the different quadrant that they're going to give us. So this table is a good thing to go get refreshed on, or it's a good thing to rewrite in your Chapter 5 notes, because it is going to play a pretty big part in us solving or manipulating around these trigonometric functions. Do we have any questions on how we did this first one? On how we used the information they gave us to algebraically get down to secant? Okay, we're going to use the same information. We're still going to deal with tangent theta is -5/3, and theta is still in quadrant 2. But this time we're going to find sine of theta. And like I said, there's a lot of different ways that we can go about this. I'm going to show you the way that I went about it and the way your book goes about it. First thing I'm going to do is I'm going to say, okay, well, they give me tangent. So is there any of my identities that deals with tangent and sine or cosine? Yes, because my quotient identity says tangent is sine over cosine. Okay, so I'm going to go with that, where tangent theta is sine theta over cosine theta. Now, my end result that I want is I want sine theta. So if I just manipulate this around to get started with, I would just multiply that cosine theta over. So that sine theta is tangent theta cosine theta. So that's nice. We can use that information. But we don't know what our cosine is, so we're still a little bit lost there. We do know what our tangent is because they give us that. So what about our cosine? Let's look back here. Well, I know from my reciprocals that cosine theta is the same thing as 1 over secant theta, right? Because secant theta is 1 over cosine theta. So I know that information. And the nice thing is the question right above, we just found out what secant theta is, right? So we can use that information to help us determine what our cosine theta is, which will then help us figure out what our sine theta is. 1 over secant theta, well, we just found out that was negative the square root of 34 over 3. And you're like, well, that's gross. Yes, it is. But don't freak out, because all we have to do is flip it to bring it up so that it's negative 3 over the square root of 34. But what's the rule about having a radical in the denominator? Yes?
You have to multiply the bottom by the top.
That's right. We can't have a radical in the denominator. We have to rationalize our denominator, which means we multiply the top and the bottom by the square root of 34. We can't just leave it. When we do that, on the bottom, it gets rid of the radical, which is the whole point. It's okay to have the radical on top. We just don't want that radical on bottom. So negative 3 square roots of 34 all over 34 is actually what cosine theta equals. So now that we know what cosine theta equals and we know what tangent theta equals, we can figure out what sine theta is. I'm going to slide up. Sine theta equals cosine theta times tangent theta. Well, we just said cosine is negative 3 square roots of 34 all over 34 times, in the original it said negative 5/3 is our tangent. The 3's cancel, the negatives cancel, leaving us with 5 square roots of 34 all over 34. And we would definitely want to check, because we are in quadrant 2, tangent in quadrant 2, or excuse me, sine in quadrant 2 is positive. So we leave it positive. Questions? All right, we're going to do one more with the same information, where tangent theta is negative 5/3 and theta is in the quadrant 2. This time we're going to find cotangent of negative theta. So then I'm going to look at the front, and I'm going to say, okay, cotangent of negative theta, and I'm looking under my even-odd identities. I know that cotangent of negative theta equals the same thing as negative cotangent of theta. So that's nice. I know from my reciprocal identities that cotangent is 1 over tangent. And they give us tangent from the very beginning. It's negative 5/3. To get that fraction out of the denominator, we're going to flip it and bring it up so that we have 3/5. Because there was a negative on top and a negative on bottom, so we don't have to worry about that. And that's all you have to do. So some of them are more complex. Like the first two examples, we had to use quite a few different identities and actually to get to the end result that we needed. But sometimes we don't have to do quite as much. We just take the information that they give us, we do some flipping, and we're good to go. I do have a little star note specifically for like the sine theta part. And it says that when you take the square root, you choose the sign based on the quadrant of the theta in the function, which is what we did. We had to check to see if sine was positive in quadrant 2. And we have to determine that as we move forward using that table from 1.4. So any questions on how we did any of those 3 different steps? Like I said, these are not the only ways to get there. So if you see a different way that you are more comfortable with using some of those identities, then that's totally okay. All right. Let's do another type of problem. We're going to write cosine x in terms of tangent x. What this means is when I get done and I get to the final product or the final answer, I only want to have things that say tangent x or tangent squared x or something like that. I don't need to have sine or cosine or anything else over there. So we're going to have to figure out how we can get there, just starting with cosine of x. Well, let's look at the front. I know cosine, just from my reciprocal. Cosine of x is 1 over secant of x. I know that. Now you're like, well, that doesn't have anything to do with tangent. You're right. Sometimes we're going to have like a middle step that we have to get to first before we can actually get to our final solution. The reason why secant x may actually be more helpful for us is because I know from my Pythagorean identity that tangent squared, I'm going to say theta, but it's x, sorry, plus 1 equals secant squared of x. So if I can get cosine to look like 1 over secant, then I can use this Pythagorean theorem identity to get us to the tangent that we're wanting to get to. So that's pretty good. So the problem here, though, is that this identity over here is in terms of secant squared, whereas this is just in terms of secant. So like you said previously, in order to get rid of the square, I would have to square root both sides. So that's what I'm going to do, because I need to get something that says secant. Okay? So I'm going to square root both sides. So that I get the square root of tangent squared x plus 1 equals secant x. We do want to put a plus or minus out here, because it doesn't tell us a specific quadrant. So we could think of this as any of the quadrants. So we do need to be careful and include the plus or minus out front. If it told us write cosine in terms of tangent x in quadrant 1 or in quadrant 2 or in quadrant 3 or whatever, then we could actually pick the specific sign for our cosine. But since we don't know which quadrant we're going to fall in, we're doing a more general example, we're going to include that plus or minus. Now that we know that secant in terms of tangent, and we know cosine is 1 over secant, we can do a substitution. We can plug all of this into the denominator over here, because cosine of x is 1 over secant, and we just said secant is this plus or minus the square root of tangent squared x plus 1. But what's the rule? Are we allowed to leave it like that? No, because we've got a radical in the denominator, so we've got to rationalize it. Here's the nice thing, though, is it doesn't really matter how complicated the underneath the radical part is. We're still just going to take the top and the bottom times that radical. Sorry, that's like really tilted. There we go. When we do that, we're going to have plus or minus the square root of tangent squared x plus 1 on top, all over tangent squared x plus 1 on bottom. And even though you're like, why would we ever do that? We did get cosine to look like tangent of x. There's tangent squareds in there, but that's okay. Cosine equals something all in terms of tangent, so we are good to go, and that is actually our stopping point. This may not seem like a useful tool, but this manipulating around of the functions is very helpful. One way to kind of think about the stuff that we're doing in this chapter and in this section specifically is kind of like what you did in college algebra when you would manipulate your linear equations around to look like y equals mx plus b. They didn't always give them to you in that form. Sometimes they gave them to you in general form, or sometimes they gave them to you with the point slope form. I was right the first time. And then you had to get them into that point intercept form. And that's really what we're doing here, is we're doing a lot of manipulating to get them into these different formats. And today, especially in 5.1, we're just doing a lot of manipulation. In 5.2, we're going to start trying to prove different trigonometric functions equal each other. And these are some of the intermediate steps that we have to use in order to get there. And so we're learning step by step how to do that. Questions on this one? Some of these, it just takes time and takes practice playing around with the different identities. And so don't think like you should just automatically know how to do all of these. Sometimes you're going to go down a rabbit hole and be like, well, this isn't really helping me, and you're going to have to try and go down a different rabbit hole for a little while and figure out which ones are going to work. It's kind of when you learned how to factor for the first time, there's some little tricks that you can kind of use, but there's still some guessing and checking and some playing around that you have to do. And this is kind of similar. The more you do this, the easier it's going to be, because you're going to start saying, okay, well, I know cosine equals this, and I know sine equals this, and let's see how we can play around with these. All right. Let's look at this one. Write 1 plus cotangent squared theta over 1 minus cosecant squared theta with sines and cosines and no quotients. I don't love the way this problem is worded. I think it's a little deceptive. So I'm going to give you a little hint in that if it says sine and cosine with no quotients, that doesn't guarantee that you're going to end up with a sine and a cosine at the end. You could end up with a cosecant or a secant at the end, because what are those? Those are the inverses of sine and cosine. So I don't totally love the way this one's worded, but the fact that it does specify that you can't have quotients, that means you can't have any type of fraction as your end result. So if you are working through this one, trying to get somewhere, and you still have a fraction, at least you know you're not quite there yet. So that is kind of nice. Okay, so we start off with some cotangents, we start off with some cosecants, and we need to get all of that stuff to go away because we just want sine and cosine. So from our page, I know that cotangent of theta is cosine of theta over sine of theta. I know this. And I know that cosecant of theta is 1 over sine theta. Those are 2 things I know. So I'm going to do some substituting and plug that information into what they originally give me. The 1 plus cotangent squared theta. I'm rewriting it so that it'll be right next to each other, so you can see what I'm substituting and where I'm doing that. So instead of writing cotangent squared theta, I'm going to write cosine squared theta over sine squared theta. Like that. And then in the denominator, instead of writing cosecant squared theta, I'm going to write 1 over sine squared theta. Now we've got a lot of fractions going on. We got fractions in the numerator, we got fractions in the denominator, and that's all inside one big fraction. So let's get rid of a little bit of the fractions that are going on by multiplying both the top and the bottom by that sine squared theta. When we do that, that's going to at least get rid of the fractions within the fractions, which makes our lives a little bit nicer. So I don't know about you, but I don't like fractions and fractions. So what you're doing is just distributing that sine squared to each of the terms in both the numerator and the denominator. So you get sine squared theta plus cosine squared theta on top over sine squared theta minus 1 on bottom. Okay, so take a look at your identities. Can somebody tell me anything they know about the top, about our numerator? It is. That's one of our Pythagorean identities. Sine squared theta plus cosine squared theta is equal to 1. So that makes that really nice. Do we know anything about our denominator? Cosine. Yeah, it's cosine squared theta. It's just a manipulation of this Pythagorean identity. So this would be cosine squared theta. Negative, sorry. Because it's backwards. So we're really close now because it said it wanted all of this mess that we started with in terms of sine and cosine, but it said no quotients. So we can't have a quotient. What is 1 over cosine squared theta? Yeah, it's secant squared theta. So this is why I didn't love the way that they worded it at the beginning, because in reality we end up with a secant squared and not a cosine or a sine, and I think that's a little bit deceptive. But that's one of the reasons I also included it in my notes, because I want you to be aware of how they're going to word things, or at least how your book words things. I haven't actually designed the homework yet, so I will try to make sure I pick ones that are very direct in what they're asking you for, so it's not going to be very ambiguous and all that kind of stuff.